Hope my screen is visible. Can someone please confirm if my screen is visible? Okay, Ganesh. Okay, so there you go. So the float data type, right? So we have covered 6 data types. Now we are going to, yesterday we have discussed about this float data type. So let me give you a quick recap, right? So for each and every data type, you are going to define any data type with the 4 key points. Point number 1 is you will talk about its size, right? The float is going to consume 4 bytes of memory, right? So I can say that the size of the float data type is 4 bytes. This is 4 bytes, which is equivalent to 32 bits of memory registry. So equivalent conversion, a byte is getting converted into bits. Secondly, the default value is 0.0 f. So when you say f, it means it is of float data type. It is going to have the whole number part as well as the fractional number part separated by the decimal point. Simple as that. The third point is, right, so the range, if you talk about range, the float data type really not going to, the range is not exactly specified, because you take integer can be defined, because integer can be defined in the range of integral values. But internally, the float data type is used to store the fractional part, right? So this fractional part, when you talk about the fractional part, for example, if I say 112 point, something like this. So this is the fractional part. This fractional part is going to be always the least significant part, right? So the float data type is designed to represent the larger part of the fractional part, right? So if you omit this, right, this really does not have any significance. So no, in the real life, right? Till 2 decimals, two fractional part, there is some significance. But after this 2 fractional part, these values don't have any significance. So no, that's why the range is not defined for the float data type. The range is not defined for the float data type. But we can say that it is designed to store up to 7 fractional values. The values after the decimal point, up to 7 fractional values, can be stored by using the float data type. Right? Today we will check this again using a small program. We will write a small program on top of this. Fourth one is the internal representation, right? Whenever you have a value, whenever you have a floating point value, right, this floating point value needs to be converted into the equivalent binary number, and that binary number needs to be stored in the memory, right? So to do this conversion, they have adopted a concept from IEEE standards, right? So it is going to use single precision. I will tell you what is single precision. Single precision, IEEE 754, right? It is using single precision IEEE 754 floating point. Point standard. I'll tell you what is single precision. And the fifth point, we can talk about what is there any other point that needs to be mentioned? Do you have any guesses? Did I miss anything? Size, default value, fractional part, range concept is not there. That's why this is replacing the range concept, and this is something new. This is something new that we are that that we have started seeing that in the float data type. Is there any other point that I have missed? I don't think so. I think this would be sufficient. Okay. Now, so today we will see one more example, because yesterday's example I don't think you got much clarity. So today I'm going to take another example to do the conversion. Before that, right, let me open the online compiler. Chrome online compiler. Right. So let me take a value. For example, in our example, I am taking float example ex equal to 1.23456789, some value, some random number I am taking, right? I am trying to print this number, print this floating point value, I can say system dot out dot print element. Let me try to access. If you look at this number, the number has only one whole number part, and it has many fractional part. There are many fractional values after the decimal point. If I run this, and we get some answer. I mean, you will get an error, because when you define a float, when you are defining a value, or when you are assigning a value to the float data type, it is mandatory, it is compulsion to define it with, to suffix it with f. This is a compulsion. Try to understand, right? When you are assigning a floating point value to a variable on top of float data type, right? It is compulsory to suffix that value with the letter f. Let me run this once again. So we are getting an answer, and if you look at this answer, right, some of the values are not printed. You see, only the values up to 9 is printed, and 1 2 is missing here, right? If you count this fractional part, you can see 7 fractional values after the decimal point. 1 2 3 4 5 6 7 7 fractional value, and the one whole number value. Before the decimal point, whole number value is there, and after the decimal point, 7 fractional values are getting printed. In total, right, including this fractional as well as the integer value, 8 values are getting printed, 8 values are getting considered, right? Let me move the place, let me move the point to point here. Let me shift the point to right, to one value towards the right. Now it's 12.34567. If you see the output, if I run this again, right, now only 6 decimal values are considered. Sorry, 6 fractional values are considered after the decimal point. In total, 8 values are there. Right? Two whole number part and 6 fractional values part. Right? If I shift the number, if I shift the point towards the right, now 123 point some value, I run this, right, 123 point. So it is now it has become 5 values. I keep doing like this, it will become 4, right? At one point of time, right, let me keep a point by considering the 8 whole number part, 1 2 3 4 5 6 7 8. I'm keeping the point here. So now it is getting represented in the form of scientific notation. Can you see e to the power of 7, right? So we can conclude that, right, the floating point data type is going to consider 8 values, including the whole number part as well as the fractional part. 8 values it will consider to be printed at any point of time, right? If you consider this scenario, right, if you are keeping the point by considering the 8 values of the whole number part, right, the output is getting represented in the form of scientific notation. If not, by least, like maximum fractional part values can be 7 in this case. 1 point. If I do this, I at maximum we can get 7 values. We can also do this 0 point something. Now maximum what? 8. But the idea here is the whole number part. To calculate the whole number values as well as the fractional values, it will be 8. It will be 8 values. It's going to consider 8 values, right? If you are keeping the point, if you are representing the whole number part with 8 with 8 positional values, then the output is going to be represented in the form of scientific notation, right? This is just an observation, right? This is a deep observation how the output is getting displayed in the console. It depends upon the way you represent the input value, right? So the takeaway, the bottom line is very simple. Totally 8 values will be printed in the console, right? It can be no matter how many whole number part is there, how many fractional part is there, depending upon the input that you give, that will be compiled, and during the execution, the output is going to get represented in this form. And if you count the values, right, in total it is 8. If I do this, if I keep shifting the number, the size is going to be very concise. It is going to get reduced. 1 minute. Did I miss? Okay, this is something not be there. Okay. Right. Scientific notation. Scientific notation. Okay. This is a simple observation. Now we will understand. For example, let us take this example. I have a value 45.45. And we know, by looking at this, we know, I made a mistake. We should suffix it with F. So output is 45.45. But we will understand how this 45.45 is getting converted into the binary number and getting stored in the memory register. So this is the second example following the first example which we have discussed yesterday. Pay some attention. This is going to be very interesting. Okay. This is our program. Right. Let me reduce, make some space. Okay. Right. Hello world dot Java. It should be saved as, it should be saved with .java extension. We know this, which is called as the source code. Then compiler will come into the picture, right? So this is the compiler. We are just doing the tracing part. So we will do this. We will do this every time. Every time we are going to do this. At one point of time, we are going to, we are not going to consider these things. We need to get used to this to understand how these things are working internally. Compiler, okay, compiler will try to compile this .java file. So it requires this .java file. Okay, right? It will check for errors. If the source file is error free, it will generate what? It will generate a .class file. Hello world .class file will be generated, right? Then execution. JVM will be used for the execution, right? JVM, we need to load, this needs to be loaded inside the JVM. Hello world.class file will be loaded inside the JVM. Let us do that. Okay, this is loaded. As soon as this is loaded, main thread will be created. Thread. So when I say thread, it means a kind of control. So this main thread will try to get access to our main method, and all the instructions inside the main method will get executed. So we have two instructions, right? Now we will understand. So the first instruction says we have defined a value to a variable ex and declared it on top of float data type. Right? This thing needs to be stored inside the memory. This is a data, a value, right? This value needs to be stored inside the memory. Right? That's what the purpose of primitive data types. Whenever you are using the primitive data types, we are assigning a value, or we can say that we are assigning a data to that primitive data type. Right? It is not like just the data is getting assigned internally, right? This is going to consume some memory. Right? Here I am talking about float. So internally, float is going to consume 4 bytes of memory. Means 32 bits of registry will be created. Right? So in our previous approaches for all the integer data types, right? So the value will get converted to the binary format directly. But this is not something. This is something very new. So we are. If you look at this value, the value is in the form of floating point value. It has the whole number part and it has the fractional part. There should be a way, right, to store this value inside the memory. Right? Java is following one standard approach. Not only Java, so many programming languages are following one standard approach. So this is a standard approach. The standard approach says Java is following IEEE 754 floating point standards. Right? This IEEE 754 floating point standard, when you talk about this, right, it is going to convert this value or data into the binary number by following the standard, and it has 3 protocols, or we can say that it has 3 steps that one has to follow to achieve this. Right? Step number 1. Okay, so now before even proceeding with that, a registry will be created. So this is how the registry is going to be. Let me keep the registry like this. Each 4 bytes, right? So each and every byte is a collection of 8 bits. So we get 8 bits. 1, 2, 3, 4, 5, 6. Okay, 8 bits. Let me replicate this. So 8 4 is 32. So we need 32 bits of registry. Okay, we got 32 bits of registry. Okay. So now the duty of the computer or the machine that you are using, right? It has to convert this floating point number to the equivalent binary number, and all the spaces, all these bits needs to be filled. How the conversion is going to happen? How these things will be represented internally? Right? That's what we are trying to understand. This is the memory, right? Memory is created. Now we need to do the conversion. Usually we don't do the conversion. We are understanding the internal things. Try to understand it. Right? So step 1. Step 1 is very straightforward. Convert the whole number part to the binary and the fractional part to the binary, the equivalent binary number. How to achieve this conversion? Our number is 45.45. So let us take this. First convert this 45 to the equivalent binary number. So we know the conversion 45. Keep dividing it by 2. So 2 times, 2 times. Remainder is going to be 1. 2 11 times. Remainder is going to be 0. 2 5s. Remainder is 1. 2 2s. Remainder is 1. Right. 2 ones, remainder is 0, right? And write the number from bottom to top order, right? Very straightforward. I don't think you need much explanation on this. So 1 0 1 1 0 1, and the base is going to be 2. So this part completed, right? Now the fractional part 45, right? 45. So this is the fractional part. So we are going to follow a different approach. For the whole number part, we keep dividing it by 2. For the fractional part, we keep multiplying it by 2. That is the bottom line. So 0.45 into 2, right? It gives what? Instead of 0.45, I take 0.45 into 2 is going to be what? 0.9, right? And keep track of this number, 0, right? And again, take the resultant. This is the resultant value, and multiply that resultant value with what? With 2, right? Now we get what? 1.8, right? Keep track of this number or extract this number, right? So we don't take 1.8 this time, right? We will consider only what? Only the fractional part, 0.8, right? So 0.8. So 0.8 is also, it can also be represented like 0.8. Both are same, right? So again we get what? 1.6. Extract this number 1, right? Now we don't take 1.6. Instead of that, we take 0.6 into 2, right? We get what? 1.2, right? Extract this 1, and there you go, 1.2. Again 1.2 we don't take, 0.2 into 2 times 0.4, extract this 0. So again 0.4 into 2 times, what we get? 0.8, right? Extract this 0. Again 0.8 into 2 times, we get what? 1.6. Extract this 1. So let me stop here, because if you see the pattern, so this is the pattern 1.6. This step is similar to this step. Don't you think so? Right? If I repeat this, it means the next consecutive numbers, next consecutive values is going to be this itself, isn't it? Right? So it goes just like that infinitely. It has no end. It keeps going forever. Yes or no? So let me let us read these numbers from top. Let us write this number from top to bottom. Previously, for division, we followed bottom to top approach. This is a multiplication approach. We follow top to bottom, right? So the extracted numbers from top to bottom is 0, 1, 1, 1, 0, 0, right? And again, so it is like 1, 1, 0, 0, 1, 1, 0, 0. So I am adding a bar over here because this gets repeated. So 1, 1, 0, 0, and this 1, 1, 0 is going to get repeated. Instead of writing that, I am just using a bar on top of it. It means it is a repetition, right? Now if you see, we have found these two, right? Step 1 is completed. 45.45. So if you write that in the form of a binary representation, this is how it will be written: 1, 0, 1, 1, 0, 1. Whole number part dot 0, 1, 1, 1, 0, 0, 1, 1, 0, 0. Correct me if I am doing any mistakes. Okay, 0, 0, 1, 1, 0, 0. This is what? This is fractional part. Right? Understood till now? Type something in the chat box. We'll discuss about this step. You have understood so far? Type yes or okay. Okay. So let us copy this number for our reference. Okay, I cannot copy this. Step 1 is completed. So this is what we got from the step 1. Okay, now step 2. Step 2 says, so before even understanding the step 2, we will understand something about the scientific notation. Okay. Step 2 says we need to convert this number to what? To scientific notation. To scientific notation. How do we achieve that? Right? Why scientific notation? The question arises, isn't it? So scientific notation is a way of representing a number, way of representing a larger number or a very smaller number. Right? So these numbers will be represented to make it very readable. Right? For example, let us say that I have a number like this is just an example. Let us say that I have a number like 1 thousands, 10,000, lakhs, 10 lakhs, crores, 10 crores, 100 crores, 1,000 crores, 10,000 crores, lakhs crores. This is a very big number, very big integral number, right? If I want to represent this into the scientific notation, right? So this number can also be written like into 10 to the power of 0, both are same. So the value of 10 to the power of 0 is 1. So anything into 1 is the number itself, right? Right. So if I if I generate a point, usually this is where the location of the point is, right? If I keep shifting the point towards its left, right? So for this is where the point is going to be imaginarily. So this point is not visible, but when you want to include a point, this is where you will include, isn't it? Right? If you want to shift this point to one position to its left, right? You will be increasing this 10 to the power of 0 as 10 to the power of 1. Right? 2 positions 10 to the power of 2. 3 positions 4, 5, 6, 7, 8, 9, 10, 11, 12. This is going to be 10 to the power of 1. Right? So this number can be 1 into 10 to the power of 2. This is very much readable, yes or no? This is what the actual purpose of representing a large number in the form of scientific notation, because we can achieve the readability. Even though the number can be a huge amount of number, secondary, to convert this into the scientific notation, the readability will be improved. Right? So the same thing goes for the fractional part as well. Right? If I have a big fractional number like 0.000001,276, right, into 10 to the power of 0, right? If I want to shift this number to the right towards its right, means if I want to shift this point towards its right, right? So if I shift one place, we should do -1. 2 places -2, -3, -4, -5, -6, -7, -8, -9. Right? It's going to be become -9. Right? Now this number can be converted to what? 127.6 to 10 to the power of -9. This is how the decimal numbers can be converted for the readability. Likewise, same example goes for the binary numbers also. So let us convert this to the scientific notation. So this number we need to convert it towards scientific notation. So decimal point is here, right? So our job is to shift this decimal point towards its left. So 1 position, 2 position, 3, 4, 5 position towards its left. If I do that, right, if I shift this decimal point towards its left to 5 positions, so this same number can be represented like now 1.01101, right, 0.1.0 into, so since it is a binary representation, we do 2 to the power of, right? So we need to add bar here. I forgot to add this because this number is repeating, isn't it? Repetitive. Go back here. There is a bar. Last 4 digits as a. So this last 4 digits are extra. Right? So second thing is also done. First step is convert the whole number part as well as the fractional part into the equivalent binary number. Then the binary value that you have got needs to be converted to the scientific notation. So this is a scientific notation. Right? The third step, right? Before understanding the third step, so this is representing about this part is, we call this part as mantissa. And we call this part as exponent. Right? And we call this, since this number is a sign number, right? So for a negative number, the signature is going to be 1. For the positive number, the signature is going to be 0. And keep this in mind, this is mantissa and this is exponent. Right? So if you talk about this exponent, now let me go back to that registry. This is the registry. The first positional value, the leftmost bit or the most significant bit is always reserved for what? For the signature. This is for signature. Right? Remaining 8 bits, 1, 2, 3, 4, 5, 6, 7, 8 is registered for exponent. Right? The remaining 23 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 is registered for mantissa. Right? So the first bit, let us talk about this MSB. So if you look at the number 45.45 is a positive number. So the MSB is going to be what? 0. Yes or no? MSB is going to be 0. Right? The remaining next 8 bits is for exponent. In our case, the value of exponent is what? 5. 5 is the exponent value. But you cannot directly write, just you cannot convert this 5 to the binary number, and this number cannot be filled in the place of exponent registry. Instead, there is a concept called bias. For now, we will learn this on the go. But for now, the value of bias is 127. Right? Just assume it like this. If the exponent is positive number, add that positive number to this. But if the exponent is negative number, do the subtraction, as simple as that. Right? With the bias, and if the exponent value is a positive number, add that with the bias number. If it is a negative number, subtract that with the bias number. In our case, we will be getting what? 132 after the addition. Right? Now convert this 132 to the equivalent binary number, and store that binary number in this exponent position over here. Right? Shall we do that? We have 132. Right? So I don't think we need much explanation on this. 132 divided by 2, 2 6 times. right? Again 6. Balance is 0. 33 times 0, 2 ones, 2 6, 1, 8. We get what? 0, 2 fours, 0, 2 twos, 0, 2 ones, 0. Bottom to top, 1, 2, 3, 4, 5, 6, 7. Right? So we have this number. This number needs to be filled in the place of the exponent register. So 1 followed by 4 zeros, again 1 followed by 2 zeros. So 1 followed by 4 zeros and again 1 followed by 2 zeros. This part is completed. The remaining part is a mantissa part or the fractional part. Yes or no? Right? So this is the fractional part, isn't it? This is the mantissa part. Let us copy this. Or okay. Okay. Let us fill this. This from here, right? 0 1 1 0 to 0 1 1 0 1 0 1 1 1 0 1 1 and again 0 0 0 0. This is a repetitive 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1. There you go. So this is how it gets represented. The 45.45 needs this many steps to get stored in the memory register. So the values will be stored in the memory register. So far, right, we have first line is completed. Now second line we are trying to get access. After getting stored in the memory registry, right, this ex variable will be pointing to this memory registry. Right. Now we are trying to access this element. Second line, we are trying to do what? We are trying to do the access. Right. So to do the access, and again this number needs to be converted to what? Equivalent decimal number. The reverse procedure that we will see tomorrow. Right? If I take that today, and it is going to create some confusion in your understanding. I do not want to do that. Right? Now tell me if this is clear or not. Hello, Darshini, Shashwat, Samyukta, Ganesh. Is this clear? Right. And you should also understand one more thing, right? See, no one is going to ask you about this conversion, but the actual idea here is like when you are giving the definition for the float data type in Java, right? If someone is asking you to define the float data type, right? You give these points, right? This is the points that you deliver, right? So delivering this point is okay, but if you look at this single precision IEEE 750 floating point, right? When you say this, there are high chances that you might be asked the follow-up question: What is IEEE 754 floating point standard, right? So you can understand this only if you understand this. Right? IEEE floating point standard is nothing but converting the floating point number to the equivalent binary number by following these three approaches, right? And this is the standard way of standard approach. This is standard approach that is being followed by many languages, and Java is also one among them. Right? Now the question is, what is the single precision? Right? Single precision. What is the single precision? What does it really mean? Let me explain you. Single precision talks about the memory registry. Our I know in Java the memory registry for floating point is 32 bits. So single precision. In Python, to take the floating point is going to occupy 64 bits of registry. So over there they call it as double precision. In some other languages, right, the floating point data will be represented, or it is going to consume 16 bits of memory. This is called as off precision. Hope you are able to understand. Right? This is just a representation. For 32 bits of registry, we can also call it a single precision. For 64 bits, double precision. For 16 bits, off precision. So no need to get any confusion. Single precision. This is how the single precision is. Other way of defining the single precision. Right? And in Java, the double data type is also called as the double precision data type because it is going to consume 64 bits of register or memory space. Right? And one more thing, is there any other way to find the minimum and maximum values for any data type? There is a way. I will help you with that. Just type system.out.println. This is the predefined way. Byte dot in underscore value. You will get the minimum value for byte. Right? Byte dot. Instead of doing the calculation by yourself, you can also achieve this just by this way. For the byte data type, the minimum value is this, maximum value is this. Likewise, for short, let me replace that with short. Minimum, maximum we want. Let me replace that with integer. Minimum, maximum. Let me do long. The four popular data types, right? Integer, byte, short, long. So are the four popular data types that is usually represent the numbers for long. Right? And for float, I said float has no such thing, right? But internally, they have also considered the minimum and value in the form of scientific notation. So it is being dealt with the form of scientific notation, but only for the fractional part. You don't need to say in the interview room, if they are asking you what is the size of the float data type, right? You can just say this. There is no predefined size, but it is designed to store up to 7 fractional values. The size is not defined actually. It's the arbitrary thing that the compiler is getting generated. Right? In theory books, you don't find the exact size for the float. And for the double, we haven't discussed yet, so I'm just giving you the idea. Minimum value and the maximum value. Again, for the double also, the size is not defined. Right? It is capable enough to store the 14 to 15 fractional values. Double. And what is left? Character data type. Character, minimum, maximum. So for character, what is it? Get a mistake here. The character minimum value is always it is printing the Unicode value not the actual number is getting printed, it is printing the Unicode. Like I said, why it is going, they are always going to print the Unicode value because the numerical value will not be displayed. Internally, the number will be converted to the Unicode, and Unicode will be converted to hexadecimal, and the hexadecimal will be converted to a equivalent binary number, and while extracting it, the equivalent character will be displayed. See that video once again, you will understand. And at last, what is the data type? Boolean. Do we have like concept of minimum and maximum for Boolean data type? Can you tell me? Do we have a concept of minimum and maximum values for the Boolean data type? Any idea, Ganesh, Samyukta, Darshini, Sashwant? Hello? You can say yes, or you can say no, or you can say don't know. Three possible answers are there. Yes or no or don't know. The question is, do we have any minimum value or the maximum value for the Boolean data type? Such thing is there or not? Don't know, sir. Okay. Yeah. See, Ganesh, you are right, because there is no such thing for Boolean. We say I have already defined that Boolean is going to represent the values in the form of true and false, right? So we get error. So there is no minimum value, there is no range that we have discussed about this Boolean data type. As it will represent either true or false. So the concept of minimum or maximum will not exist there. That's why we are getting this error. Right? So this is not applicable for Boolean. For the remaining data types, it is applicable, right? You can try this out. I will share this with you. Chat box. Right? This is another way of getting the minimum and maximum value for the primitive data types. It has been shared in the chat box. So the quick recap, right? Float data type. The size is 4 byte, 32 bits. Default value, okay, 0.0. When I say default value, we have already know the concept of DIA. So DIA is applicable for the methods. When you are declaring the values inside the method, you should follow the DIA approach: declaration, initialization, and what accessing. Right. So when you want to get the default value, the value needs to be initialized outside the method. In this case, float number, right? So I am using the data type, I am using the variable, but I am not defining or assigning any value to this particular variable. Taking static for the time being, I have already said that whenever I am declaring a variable outside the method, right, for the time being, we have to keep it as static. Why we will keep it as static, we will discuss that in the future classes. When I try to access this, system.out.println number, we'll get a value 0.0, right? Even though we get 0.0, the suffix f is not going to get printed. Understand that? The suffix f is not going to get printed. Sir, what is the proof? Right? Let me say, now I am assigning a value 1000.34. Right? The system is going to eliminate the suffix f. Doesn't mean that the f is not there. F is there, but it is not visible to us. As simple as that. Right? While displaying, it is not being displayed. It doesn't mean that f is not. F is there. Right? So if you see any theory proofs, they used to mention that the default value of float is 0.0 f. Right? Even if you, it is mandatory for us to give f. But when the system is displaying the output, for the system it is not mandatory. Doesn't mean that f is not there. F is there. That's why it is 0.0. And it is designed to store up to 7 fractional values and single precision. We got to know what is this. And this is a simple program. right? Only for this particular line, like internally, this many conversions are happening. It's step 1, that is step 2. Step 2 is finding what the converting the equivalent binary value to the scientific notation. The step 3 is what? Placing the values in the registry. This is for signed, this is for exponent, and this is representing what? Mantissa. Right? And again, exponent, you cannot convert the number directly. You need to use bias. Bias is what? 127. It is a positive number, add 127 plus that exponent value. If it is a negative number, you do subtract. After doing this, you get what? 132. Now you do the conversion decimal to binary, you will get a value. This value will be used to fill this registry. And as simple as that. We are good to go. Tomorrow we are going to see how to do the reverse conversion from binary to decimal. From this binary to decimal, we will see that tomorrow. Right? After that, the double concept is very simple. If you understand float, you will understand double. Right? Then we will start discussing about operators. Right? Any questions for me?